Hello everyone. Welcome to our new meeting. And my project is on the access internal multiple attenuation algorithm for a 3D source and 1D Earth, one-dimensional Earth surface. Here's my outline. And firstly, I would like to state the motivation of this project. And then I will introduce this reduced form of 3D access internal multiple attenuator, which assumes a 3D source for a 1D layered Earth. And after that, I will show you some initial numerical results for this to test this reduced form of 3D internal multiple attenuator. And finally, is the conclusion. So we start from the motivation of this project. Okay, we would like to point out that there are onshore and offshore regions which are close to 1D Earth and have serious internal multiple problems. For example, Central North Sea and Canada and offshore Brazil and the Middle East. When the Earth is close to 1D, we do not have to pay for a complete data set and high computational as in the 3D Earth by using the reduced form, reduced 3D source 1D Earth algorithm. I will show you that algorithm in the second part of this presentation. And finally, corresponding to the work in our group, the 3D source 1D Earth ISS attenuator is needed for the ISS eliminator of internal multiple. Okay. Let me introduce a little bit about the current state of ISS internal multiple attenuator. Okay, current state of 1D Earth ISS attenuator is the algorithm is derived from the 2D source 2D ISS attenuator, which means we assume a 2D line source. So I give a brief concept of 2D line source here. 2D algorithm assume that whole world is 2D, so one point cells in the 2D world is a line in the 3D. And you will see a tail in the events of the 3D data because of the nature of the 2D Green's function. Okay, so this algorithm is pioneered by Arrujo 1994 and Weglein 1997. And our group has the code released by Dr. Turinki and Dr. Kaplan. And also, we have successfully applied this 2D source and 1D Earth algorithm into the field data, as my colleague Chang Fu has shown to you yesterday. The Canadian in Canada data, and that part is also in our annual report in this year. And for a more realistic and more complete acquisition in the real world, we have to consider the 3D source. So in this presentation, we will reduce the 3D access attenuator, which means we assume the 3D source at first. And here is a brief concept of the 3D point source. And in the 3D theory, which here means our 3D attenuator, in the 3D theory, the world is considered as 3D. So the source is a point in a 3D world. Okay, for different Earths, different kind of Earth, we have different requirements from asked by our algorithm. For 3D source, 3D Earth, which is the most complicated case, our algorithm, our attenuator requires the coverage of both the sources and the receivers, which means you have to do the acquisition of the shot together along the x direction and also along the y direction. Eventually, you have full coverage of the sources and the receivers. on this area you're interested in. And if you have a singular Earth, you have a 2D Earth. You have a 2D Earth. Our algorithm requires the shots along the direction perpendicular to the direction doesn't vary, the probability on which the probability doesn't vary. So you have to have a single line, sources on a single line along the x. Here is defined as x direction. Also, usually people call it inline direction, and the area coverage of receivers. Even for a 1D Earth, if you consider the 3D source in it, in Cartesian coordinates, you can't avoid this coverage of receivers, which means our algorithm asks you to have one single source, but also the area coverage of the receivers to obtain the kx and the ky in Cartesian coordinates. In this presentation, we will try to rewrite this algorithm in cylindrical coordinates, which can reduce the math tell us which can reduce this requirement of the data. We only need one in this coordinates, cylindrical coordinates. We only need one single source, and the receivers on one single line. And please notice that this single source is on the receiver line, which means the y offset is 0 here. Okay. So in summary, this part, 1D Earth 3D source. Current algorithm requires a short record with area coverage of receivers, which means all the xg and yg for fixed source, xs and ys. In this presentation, the SS internal multiple attenuator will be changed into cylindrical coordinates for 3D source and 1D Earth, which allows a single source and the receivers on a single line, rather than this full coverage of full area coverage of receivers. Okay, and also this presentation will examine what difference the 3D source attenuation, this reduced form, makes versus the current 2D line source algorithm for data generated by 3D source and 1D Earth. The difference will be amplified when the attenuator enters the eliminator algorithm, which is presented by my colleague Yanglei, and the eliminator part is a very important step in the three-pronged strategy. I'm sorry. Okay. Here is the three-pronged strategy proposed by Dr. Weglein in 2013. The first part is the pre-processing for onshore applications, which has been presented by my colleagues Jing Wu and Lin Tang. The second part, we want to find the algorithm beyond the SS attenuator. And in the first part, we start our investigation of elimination from 1D Earth. So for a more realistic case, we start our attenuator for 3D source 1D Earth at first. Okay. In the next section, I will give you the reduced form of the 3D internal multiple attenuator for 1D layered Earth. In the cylindrical coordinates, use circular symmetry. Okay, what is the circular symmetry? In the cylindrical coordinates, the 3D source 1D Earth data only depends on the offside and the frequency, which is the circular symmetry under the cylindrical coordinates. In other words, it's independent of angle. The angle is not the angle. The angle is the angle of the differential vector between the source location vector and the receiver location vector. We define it as RH in the later. So from Cartesian, to cylindrical coordinates. Okay, we can see here the data only depends on the difference, the radiation part of this difference between the offset between the receiver and the source, which is defined by RH here, and independent of the angle of RH. So we use the 3D 1D E to represent this superscript to represent the 3D source 1D Earth case. And this circular symmetry we'll be saying after a 2D Fourier transform or Fourier Basel transform, because we are talking about 1D Earth, so these two transform in this case are equivalent. And we apply this symmetry to B1. We skip many math steps here, but that's what we did for reduced form. Apply the symmetry to B1 gives a product of B1 3D 1D Earth and a symmetry factor, which this symmetry factor contains a delta function. I refer you to my report to this part. And finally, after we use this kind of symmetry, we can reduce the 3D as internal multiple attenuator for 1D Earth. Okay, here is the form we reduced from the 3D as attenuation algorithm. So you can see here the B3, you can see there is no lateral integral here. All the lateral integral has been, and we can get rid of the lateral integral in this cylindrical coordinates. And naturally, our B3 needs to bind to a spatial time domain from the frequency from the wave number frequency domain. So when we use the transform, we need to pay attention to that. This transform is a Fourier Basel transform over B3, which means the reduced 3D algorithm in the spatial frequency domain is the Hankel transform, or we say Fourier Basel transform over the B3 term. And in this case, B3 is independent of angle, and the angle integral will give you a G0, which is a Basel function here. And really, this kind of transform is called the Hankel transform. Okay, I would like to give you a brief workflow for how to deal with this data generated by 3D source from 1D Earth. First thing is the 3D source 1D Earth data. Then you do the Hankel transform to make it in the frequency domain, and then you do the B1 according to the definition, and plug this B1 into the B3 algorithm. After that, after you have the B3, you need to do the inverse Hankel transform. Or if you consider the efficiency of the computational cost, you can use asymptotic Basel function, which gives you a Fourier transform kernel here, which can reduce the computational cost. But basically, this asymptotic Basel function is a far-field. It's a far-field approximation. Okay. From what here, to compare this 3D reduced 3D algorithm and the current 2D source algorithm, we make this chart. And you can see our assumption is both for 1D and in 2D algorithm, the reduced form 2D algorithm, we have the expression for B3 here. And after we got the B3, we need to do the Fourier transform to transform the B3 back to the spatial domain. And for 3D source, this is the reduced form. These two forms looks similar, so is a good news for us because we don't have to modify that main part by the prediction, multiple prediction part in the frequency domain. But when you come back to the spatial domain, you need to do the inverse Hankel transform, or you use some asymptotic form of Hankel transform. Okay, so let me make these comments. From the above chart, we can conclude that the 3D source as internal multiple attenuation algorithm remains its merits for 1D Earth, since the prediction kernel doesn't change, which means we need to prepare our data from spatial domain to frequency domain by Hankel transform, and then do the same thing as before. You don't have to modify your prediction code. After that, your output need to do the inverse Hankel transform back to the spatial domain, so that you will have the signature, the 3D source signature in your prediction. Okay. So after that, I did the initial numerical test. Here is the model I used for the testing. I used a 3D source, generated the reflected waves in a simple two reflector model, and all my source, and then I generated only one shock gather. My source and the receivers are on the same depths. Okay. And here are the assumptions in my numerical test. First is this is a 1D Earth, and we use a 3D source. This source is on the streamer. There's no lateral offset, which means, okay, we can put the KR equals to KX here. Okay, and we transform our data from spatial frequency domain to the wave number frequency domain by using a Hankel transform, or we see the Fourier Bessel transform before the prediction, which means our B1 is correct. And the data, our data is generated in KQ domain by an analytical form. Okay, here is the result. The left top one is my 3D source, here's a 3D source 1D Earth data set on one streamer, and this figure on the right side is the 3D SS internal multiple prediction, which is transformed back to the spatial domain by Hankel transform. And the one below the Hankel transform one is also the 3D prediction, which is transformed back by a more efficient asymptotic Bessel function. And the left side, on the left side, bottom one, this one is the prediction generated by a 2D SS internal multiple prediction. So we can see the difference by trees comparison here. Okay, firstly, I pick up one near outside trace, the trace number 2 here, and the right line in this figure is a 3D data, and the black line in this figure is the 3D prediction transformed back to spatial domain by Hankel transform, and the green line in this figure is the 3D prediction transformed back using an asymptotic Bessel. And the blue line here is the 2D prediction transformed by transformed back to spatial domain by the Fourier transform. So you can see the difference of this predicted event, this forced internal multiple. Let's say the 3D and 2D prediction detail in large scale. Okay, you can see the dramatic difference between the 3D prediction and the 2D prediction. And you can see here the 3D prediction is still, the amplitude of 3D prediction is still smaller than our original data because it's an attenuator here. And for this near outside the prediction using asymptotic base cell, you can see the amplitude is even smaller than the Hankel transform 1. No more Hankel transform 1. Okay, let's enlarge this 3D prediction part. You can see the difference here, and the shape of this event is spike. We use the full bandwidth data. Okay, so next step, I pick up one far offside trace number 80, and show the same thing. First is the red line. Red line is the 3D data, and the 3D prediction transformed back by Hankel transform by the black line, and the green line is the transform using an asymptotic base cell. And you can see again this 2D prediction have enlarged amplitude. Okay, the first in order internal multiple. Here, we enlarge the scale for the prediction part, and we can see the difference. Again, we can enlarge these 3D prediction detail. Okay, in this case, the 3D prediction transformed back by asymptotic base cell is close to the amplitude is close to the 3D prediction transformed back to spatial domain by Hankel transform. So we can see the green line and the black line, they are close, the amplitudes are close, and both of them have the correct time prediction. Okay, here's my conclusion. The 3D SS internal multiple attenuation algorithm can be reduced to a simpler form in order to process the data that is generated by a 3D point source and the 1D surface subsurface. The simple form requires only one source and the receivers on one single line instead of area coverage of the receivers. And this initial test demonstrates that for the data from a 3D source and the 1D Earth, use an SS internal multiple attenuation algorithm designed for a 2D line source and the 1D Earth could make the multiple problem worse. Yes, you may have the risk to producing a larger multiple than the original. In this 3D source 1D Earth algorithm, always attenuates the internal multiple in the data from the 3D from the 3D source and the 1D Earth. And it is important to understand in this developing an SS internal multiple attenuator on field data in the future where the Earth is close to 1D. And thanks to Dr. Terinki. Dr. Terinki has produced several SS internal multiple codes at M-OSRP, and the one code reduced 2D SS internal multiple attenuator, 2D source, 2D Earth, reduce that to a 2D source, 1D Earth. So that work starts with, but this work starts with 3D source. Assume a 3D source SS internal multiple, and then do the same thing, reduce it to a 1D Earth, and the data requirement is same. The paper shows that this work represents more than an increase in the effectiveness when the data is generated by a 3D source and a 1D Earth. It changes from can make it worse and to make the thing better. So I want to thank all the sponsors for M-OSRP, and I want to thank all my colleagues and Dr. Weglein for the help in my project. Thank you.